Rao for the invitation. Thank you for all your kind words during this introduction. And thank you for giving me the opportunity to be part of your faculty development program. So it's my honor to be involved in it and to share with you some of our thoughts and some of our research results in this area of trying to connect more of the unconnected or underconnected. So let me share my screen.
Sir, if you would allow me, we would like to introduce you to the panelists as well as the participants.
Okay.
May I request Dr. Satish to introduce yourself to the all participants.
Thank you, sir. Good morning. On behalf of SRM University AP and as a coordinator, I, Dr. Satish Tiwari, welcome you all to the Faculty Development Program on recent advancements in the optical communication.
Okay. Should I start now?
I think they want to introduce, there is some interruption.
Okay.
So let's wait. Mr. Satish.
Can you hear me?
Yeah, now we can hear you. So please go ahead and introduce our honorable chief guest.
Okay, thank you, sir. Good morning. On behalf of SRM University AP and as a coordinator, I, Dr. Satish Tiwari, welcome you all to the Faculty Development Program on recent advancement in the optical communication and wireless networks organized by the Department of Electronics and Communication Engineering. Especially, I thank VC Professor V.S. Rao sir and our head of the department, Dr. Ramesh Vaddi sir, for welcoming this FDP event. I also acknowledge the presence of all the faculties and participants to be part of this event. On the occasion of inaugural day of our FDP, we have a keynote talk on towards connecting the remaining 3+ billion, which will be delivered by Professor M.S. Aloni sir. Professor M.S. Aloni was born in Tunis, Tunisia. He received the PhD degree in electrical engineering from the California Institute of Technology, Caltech, in 1998. He served as a faculty member at the University of Minnesota, then in Texas A&M University at Qatar, before joining in 2019 the King Abdullah University of Science and Technology, where he is now a distinguished professor of electrical and computer engineering. Professor Aloni is a fellow of the IEEE and Optica, formerly the Optical Society of America. He is currently interested in addressing the technical challenges associated with the uneven distribution, access to, and use of information and communication technologies in rural, low-income, disaster, and/or hard-to-reach areas. Today, his keynote talk aims to provide an envisioned picture of 6G, serve as a research guideline in the beyond 5G era, and go over the recently proposed network convergence-based solution to provide high-speed connectivity in undercovered areas in order to serve and contribute to the development of far-flung regions. Now I welcome Professor M.S. Aloni sir to deliver the keynote talk.
Thank you again for this invitation, for this introduction, and for giving me and my group this opportunity to share with you some of our recent research finding in this area of trying to better connect the unconnected. And we see this particular area of research as an interesting area to make some new contribution, but also an opportunity to have an impact in our emerging and future connected societies. So as you all know, we are, worldwide, aggressively, let's say, deploying 5G. And as this deployment of 5G is happening, from an academic research, industrial research perspective, people are already working on beyond 5G and 6G. As you know, it's a 10-year cycle. And as a new generation gets, let's say, deployed, we, as researchers, we start thinking, brainstorming, thinking about how the next generation would look like. So 6G, of course, is going to be aiming to kind of push the envelope in terms of trying to come up with networks that can go for higher speeds, for lower latency, for higher density of connectivity per kilometer square. This is a trend that we have been following over the last 4 or 5 decades. But 6G will have, or hopefully from our perspective, will have another important objective, which is going to try to connect more of the unconnected or underconnected in the world. Indeed, about 3 billion people are still in this category of unconnected or underconnected. And here by connectivity, we mean people or areas that have a satisfactory connectivity from a data rate perspective. So the connectivity has to be at the right speed, it has to be available, and it has, of course, to be affordable. So these are some of the conditions to make a region connected. Now, when you look at the statistics of 4G deployment, they don't look that great, as you can notice from the map in front of you, where clearly you see a strong imbalance between countries, and sometimes even within some countries, imbalance within regions. It's well known that rural areas are most affected. It's known that developing countries are more affected than other countries, and the reasons are many. I'm not going to go into here social reasons, like linked to let's say computer literacy or lack of digital content that are relevant to a particular community. But let's talk about the technical and economical reason behind this digital divide. One of them is that telecom industry work on a model that basically relies on the so-called return on investment type of model of investment, where basically the mobile network operator invests quite a bit upfront, and they are expected to get the returns by essentially deploying their equipment in highly dense, typically urban environment. So it doesn't make much business sense for them to dig and lay 100, if not thousands of kilometers of fiber optic cable to reach very sparsely populated, low-income, typically regions. In addition, we have to remind ourselves that telecom network need to operate using a power grid. So unfortunately, in many of the developing countries in the world, this power grid is either not there, in particular in some rural regions, or if it's there, it's not that reliable. So these are some of the reasons that lead to these bad statistics. And the idea is to try to better understand why do we have this chronic divide that, by the way, is not affecting only, let's say, these rural areas in developing countries or just the developing countries in general. It can affect the heart of the big cities worldwide. And here I'm talking about the slums, about the favelas of the world, where basically, again, it becomes often an affordability problem. So there is a high correlation between low income kind of neighborhood and lack of proper connectivity. So in parallel to all this, you probably have heard that there are these 17 very noble goals that have been set by the United Nations a few years ago. They are known as 17 Sustainability Development Goals, or SDGs, and they are noble goals trying to bring better education, better health, less inequality between people in the world. They are supposed to be achieved in 2030. So there is this nice kind of, let's say, synchronism or timing, because 2030 is expected to be also the year where 6G is going to start to being deployed. So the idea here is that many of us in the research community are hoping that contrary to the previous generation of wireless communication system that have been essentially driven by profit and business consideration in a kind of exclusive fashion, we hope that 6G will be driven, at least in part, by these United Nations SDGs, which means that we want to see more energy efficiency in this 6G network, less greedy from a power consumption perspective, because that has been one of the concerns of current generation of wireless network. We don't want to see any bad effect on environment and human health in terms of EMF radiations. We want this network to be more digitally inclusive and provide connectivity to more and more people. As we rely more and more on this network in our daily life, obviously we want them to be secure and preserve our privacy even more than they do today. And of course, because we rely more and more on our daily life on this network and we cannot afford anymore to lose connectivity, we want to make sure that these emerging and future networks are going to be resilient, robust, and dependable. So in other words, some of you are probably familiar with this radar map where we see the three famous use scenario of 5G: enhanced mobile broadband for extreme kind of speeds, ultra reliable and low latency communication for extreme low latency and extreme reliability for applications such as autonomous vehicles, remote surgery type of applications that require this kind of KPIs to be emphasized, or massive machine type communication, which is extreme density of connectivity for IoT or smart building type of application. These are the three typical scenarios that are advertised for 5G. 6G can be, again, the three same user scenario, maybe with extreme, with a higher expectation in terms of like peak data speed, for example, for enhanced mobile broadband. Maybe a combination of this use scenario. We may have some use scenario where we need, like, for example, real-time gaming or augmented reality, where you will need enhanced mobile broadband combined with ultra-reliable and low-latency communication. But on the top of all this, we would like to see another less kind of let's say discussed or less kind of emphasized use scenario in the past, which is this center use scenario that is about basic internet access, or if you will, trying to achieve this so-called Gaia objective, which stands for global access to the internet for all. So the idea is that obviously some of you are maybe familiar with this economic theory behind the so-called base of a pyramid, where essentially when you try to rank or categorize people by their income worldwide, you end up realizing that most of the people, or the base of the pyramid, about 4.5 billion people, are the people who are earning less than, let's say, $1,500 per year. These people who tend to be the unconnected people, the people who live in rural environment, actually constitute a huge market of creative and resilient consumer and producer that have been largely excluded from formal market. So essentially there is an opportunity to connect these people and to make them part of formal market. So it can be actually an interesting business proposition, because even if the connection can be not that expensive or not that costly per user base, given the size of this huge market, it can make business sense to connect more of these people. And on top of that, obviously, bringing connectivity to a community can bring better infrastructure, better quality of education, better healthcare. So many of these can be done remotely and can help break the so-called vicious cycle of digital divide, where you have weak development and growth in one particular area, which means that in this area there will be limited investment of service in ICT, but this also can lead to a lack of sufficient digital connectivity, and you keep kind of going into this vicious cycle until you break it and put the infrastructure needed to connect more people, and you can bring some growth and prosperity to a particular region, the same way you bring growth and prosperity to like a province, let's say, or to a particular area when you connect with a highway or with a train line. So one last comment to motivate this important work on trying to connect more people is that beyond the fact that you connect more of the unconnected, actually, if you achieve this goal of global connectivity, you can reverse this trend of seeing more migration from rural areas to urban environment and create these more and more of these mega cities worldwide and trying to smartify these cities. So in other words, what I'm trying to say, we can move out of this, in a way, narrow concept of smart cities to something broader, which is about smart villages, smart rural areas, smart hamlets, smart living in general. And this can, let's say, trigger a counter urbanization process where basically people may not need to migrate anymore. Some people, even in polluted, congested mega cities, can go back to a more rural type of environment as long as they can be very well connected and can still have decent jobs and a good health system, sometime remote, and a good education system remotely. So, connecting more people can help in many ways. Now, let's try to see what are the issues behind, the technical issues behind connecting the unconnected. So, one way to summarize technical way, in a technical fashion, the difficulty that we have in trying to connect more people is to see this graph that summarize or visualize the quality of experience, let's say in terms of high data rate and low latency, as function of the cost per user in remote low population density area. So if you look at the right-hand side of this diagram, you see that obviously optical fiber, microwave wireless link, these are point-to-point type of technologies. They tend to be quite expensive, as I mentioned earlier, and not very practical to connect sparsely populated areas. On the other hand, relying on classical geosatellites.
Modifications.
Okay, so on the other hand, using classical geosatellite type of network, as we have used very nicely for TV broadcasting, can be interesting from a cost perspective, but essentially it doesn't provide high quality of experience for internet browsing. So what we are after is this kind of upper left corner, where we would like to see a very good quality of experience with a low cost per user, even in these low density population areas, in order to achieve this interesting visionary statement made by Nikola Tesla about 100 years ago, where, as you can see, he was already thinking in a 5G and 6G terms. So one key area of development to achieve this global connectivity is integrated space, air, ground network. By space, we mean satellite type of network. By air, we mean UAVs, drones, balloons, airships. And by ground, we mean traditional terrestrial base station and access point. But the key word is integrated. We want to see this network all integrated together, so that basically from a user perspective is completely transparent. We don't know if we're connecting directly to a UAV, to a balloon, or to ground base station, and how the backhaul is done in the air. But essentially this integrated network is going to help achieve network with a big footprint, with which allow to connect deeper anywhere in the world. So let's start with backhaul type of problems. And one of the best technology to provide backhaul, especially in remote, deep rural areas, is satellite communication, which has been used already for maritime communication, to provide global connectivity, and to provide aerial communication for airplanes, helicopter, and so on. So just from a terminology perspective, when you talk about satellite communication link, typically we are talking about a feeder link. The feeder link is like a backhaul connecting the satellite to the internet backbone. And then on the user side, we have the so-called very small aperture terminal, VSAT, who are there to basically pick the signal. And that signal can be used in particular home or kind of any area of interest, and can be converted to Wi-Fi signal for multiple access within any kind of environment. So that's just a kind of a very high level explanation of backhaul type of connections. And when we talk about satellite, there are many families of satellite that are categorized depending on their orbit. So LEO satellites are essentially satellites that are at a relatively low altitude, between 500 kilometers to 1500 kilometers, but of course they are not geostationary, so they have an orbital period between 10 to 40 minutes. Typically satellites are low cost, relatively speaking, but they have a short life, and because of the fact that satellites are not in fixed location, we need to have a lot of handoffs between satellites from the ground perspective, and the ground station tend to be expensive because you need to follow the movement of the satellites. But one of the beauty of LEO technology is that it provides low delays, and as you know, there is a race now between many big tech companies such as Amazon Kuiper, Amazon trying to deploy the Kuiper constellation, or SpaceX trying to deploy the Starlink constellation. Now there is a MEO family of satellites that are operating at a higher orbit, and that essentially are somewhere in between LEO and GEO. Constellation satellite, and GEO meaning by that geostationary satellite, that are at geosynchronous compared to the Earth, which means their rotation is exactly, or orbital period, if you will, is exact 24 hours. So they look as fixed compared to the ground, but because they are at a very high altitude of roughly 36,000 kilometers, the delay can be quite big. So one interesting research area that we have been pursuing in the context of trying to connect more of the unconnected is a so-called hybrid, very high throughput satellite with site diversity technology. So let me go and explain step by step what do we mean by all of these words. So as you know, satellite communication, as I just mentioned earlier, has two sides. There is the user link side, which is here in yellow on the right-hand side. And these are now, for very high throughput satellite or VHT satellite, we are talking about satellite that can handle about 1 terabit per second processing, which is quite huge. Now, on the user side, you have multi-beam. It can be 100 beams. Each beam can have 10 to 100 gigabit per second. So obviously, these beams can be shaped in different forms, can be moving around, going where traffic need to be kind of reached or picked from. So it can touch rural areas, maritime areas, and so on. Now, all of these beams have to be multiplexed in the satellite that's acting as relay. And then eventually, through a feeder link, they have to go to a ground station that will connect the satellite and the users that are connected to the satellite to the internet backbone. Now with the current high throughput satellite, these feeder links are implemented in Ka band. Ka band, is expected to become more and more scarce for satellite communication application, at least from a feeder link perspective, because some of it may be used for user link, or some part of that spectrum may be used for the user link, but also because there will be some more and more competition between satellite network and terrestrial network for the use of this part of the spectrum. So one of the ideas being pursued is to move these feeder link to the optical domain, and basically rely on the so-called optical fiber over the air, which is free space optics, trying to connect satellite to the ground using laser links operating in the near infrared regions. So with that, of course, we have many challenges that we need to solve. One of the challenges is trying to make sure that these two ends are always pointing to each other. So that's why there is big effort in developing pointing, acquisition, tracking type of mechanism. And then on the top of that, as you may know, free space optics is quite affected by weather and atmospheric conditions. So for instance, if you have a cloud on the way that can block your signal, and as such you need so-called site diversity, which means you need to have on the ground multiple optical gateway stations. So in the case the signal gets blocked in one particular optical gateway station, it can be picked from another optical gateway station. So this is kind of description at the high level of this interesting area where there is quite a bit of contribution to be made, and hopefully quite a bit of impact that can be achieved if we are able to solve all the problems related to these hybrid, very high throughput satellite systems. As I mentioned, when we talk about satellite, there are these three families of satellite. There is geosatellites, and examples of that Viasat 1, 2, and 3, MEO, like O3b, or the other 3 billions, kind of, that's an acronym for that, which means trying to connect the other 3 billion, ACS networks, and the LEO satellites with all the competition going between the company mentioned here. Now, I would like now to give some of the, or share with you some of our research results in the area of how free space optics is used in the context of the feeder link of satellite communication system, or HAPS systems. So as I mentioned earlier, FSO can achieve terabit data rate in geocurrent turbulent channels. The main kind of technical challenge to be let's say addressed is pointing errors that are induced by beam wander and misalignment, and then the second problem is atmospheric turbulence. So these two are the kind of main research topic or research challenge that we need to address. So let's give you an example of some of the work we are doing to improve or to come up with a better path or positioning, acquisition, and tracking algorithm for FSO links. So the idea here that we've been pursuing, along with many other colleagues in the community, is to rely on detector arrays. The idea is very simple. Instead of using a single kind of detector as shown on the right here, and as you see here, when you use a single detector, obviously the single detector is in the magenta, the beam footprint is in pink, and the more dark it is, or red it is, the stronger the intensity of the beam. Obviously, ideally, you want the beam to be centered the same way as a detector, but often because of vibrations and misalignment, you have kind of an overlap, but not a full overlap. Now, in order to capture most of the beam intensity, the idea is to have not only a single detector, but multiple detector put in the form of an array. Obviously, one may argue why not use a big detector. The idea is that the issue is that the bigger the detector, the lower the sensitivity. So it's better to go for multiple small detector with high sensitivity for every detector, rather than a big detector that cannot have a strong, let's say, sensitivity. Now, once you have that, one of the issues is signal acquisition. To start with, by signal acquisition is to try to lock on the signal and make sure that the array of detector is well centered and capture most of the beam. Now, there are multiple patterns that can be used, but given the fact that we assume that there is an error that is Gaussian distributed around the center of the location of the beam, that can be determined by, let's say, GPS location of the aerial platform we're connecting to, or a LEO satellite. And basically, then you can try to use, as a popular scheme, a spiral in your kind of search of where the signal is, in order to lock on the signal. Obviously, you may go through this spiral, and you may not connect or lock on the signal because sometimes there are some misdetections. So you want to characterize the total acquisition time that you need to be able to detect your signal. This total acquisition time is equal to TS, which is a scan time, like the time it takes to go through a full round, times X, with X the number of failed attempts going through the whole scan. So it's a geometric random variable, plus TD, which is a dwell time, which is basically the time it takes to shine on one particular location to see if you are locking on the signal or not, times W, which is the fraction of time in the last successful attempt. So this acquisition time is a random variable. It is the sum of these two random variables. The first one is essentially discrete random variable. The second one we call V happens to be because of the fact that we assume Gaussian vibration in the X and Y domain. So, when you look at the magnitude of two Gaussian X and Y, you end up with Rayleigh distribution amplitude or an exponential in power. So basically, actually, you can realize quickly that V is an exponential random variable, and TU ends up to be the sum of a discrete geometric random variable with an independent exponential random variable. And you can do the math, and you can realize that you can derive the PDF of this basically acquisition time in the form of a convolution of these two distribution. And based on that, you can derive in closed form the complementary cumulative distribution function of acquisition time that is given in this expression and published in the paper cited below. What matters here to see the effect of multiple parameter on this acquisition time, complementary CDF. So this is kind of the complementary CDF of the acquisition time, which is probably that acquisition time exceeds a certain threshold, violates a certain deadline. So basically, what you can see in this left figure here or subplot is of course you increase the noise power, the more noise you have, the more you will violate your deadline. And then the nice thing you observe, the more M is the number of, let's say, array detector that you have in your receiving system. And the more array of detector you have, the lower is this basically complement CDF action time, which means you do better and better as the number of array increase as expected. Another interesting observation or realization we're able to make out of our analysis is when you plot this complementary CDF of the acquisition time as function of the beam radius. What you notice is as you make the beam radius bigger initially, you start gaining in terms of acquisition time complementary CDF because obviously the bigger is the beam, the faster you can go through a full scan. However, at some point, you start losing. And the point is, as you make the beam bigger and bigger, you lose in sensitivity. And basically, you can have more of this misdetection. And that's why you have to go through more and more full scans. And that's why then you start becoming losing. So there's a nice sweet spot where basically is an ideal beam radius that make you minimize this acquisition time complementary CDF. Now, let me now present some of our more recent results on how FSO link can be used in the context of connecting ground station to high altitude platform. These are platforms that act as pseudo-satellite in the flying in the stratosphere, and that can have a footprint of about 200 kilometer range, which is quite interesting. Is like having a big tower in the sky. So it's not really a satellite, so it's an aerial solution. And one of its main advantages that we can use as a feeder link as well as an access point, since we can connect to these hubs, so-called hubs, high altitude platform, through our regular forms. So, so here the idea is, let's assume that we're trying to connect to a satellite through this kind of FSO feeder link, but FSO has some issues, as I mentioned earlier, dealing with the sensitivity to weather and turbulence type of condition. So often you need to have an RF link as a backup. So you end up having a hybrid FSO RF transmission where FSO is by default, and then high data rate kind of connection. And if FSO link is perturbed, you switch to lower rate RF link that can maintain connectivity even in bad FSO conditions. Now, recently, some of our colleagues that are listed here, or researchers in our area, published a paper on IEEE transactional hour space and electronic systems, where they are proposing to use hubs in the middle in the stratosphere at 20 kilometer altitude to act as essentially a relay between the ground station satellite. And with that, you can shorten the hubs. You can kind of clean up the signal that went through the atmospheric turbulence, because most of the atmospheric turbulence is happening between 0 to 20 kilometers. As such, with this kind of solution, they show that they can have 4 dB gains. And actually, what we are proposing is to kind of follow on their work and basically also use a HAP. But one of our suggestion is, instead of using, let's say, HAPs in such kind of configuration where the HAPs always in the in the direct kind of in between the satellite and optical gateway station with a certain zenith angle, the idea is to try to minimize an angle. In other words, to put always the HAP on the top of the optical gateway station. And the motivation behind that is, as you minimize the angle, you are minimizing the distance between the optical gateway station and the HAPs, which means you minimize the distance that the signal, FSO signal, has to go through the atmosphere. As I mentioned to you, most of the atmospheric turbulence is happening in this kind of 0 to 20 kilometer altitude region. So if the zenith angle is quite big, then you make that kind of distance relatively big, and you suffer from more and more turbulence. The fact that you try to minimize this distance, minimize your turbulence. Of course, you may extend the distance between the HAPS satellite, but that distance is less affected by turbulence because it's above stratosphere, is above the atmosphere. So you tend to have a more stable signals. So with our proposition, we checked essentially how the parameter of turbulence evolve as function zenith angle. So we are using here a so-called gamma-gamma model to model turbulence. Gamma-gamma is a very popular model by parameterized by the parameter alpha and beta that measure the strength of the turbulence. The bigger alpha and beta, the less turbulence you have actually. So it's like the Nakagami M parameters. So as you notice here, from HAPS satellite, alpha and beta are quite high, are quite big, which means there's little turbulence between the HAPS and satellite. On the other hand, when you go from the ground to the HAPS, which is from ground to 20 kilometer altitude, with the approach that has been proposed, as the zenith angle increases, alpha and beta decrease drastically, which means you have stronger and stronger turbulence. Whereas in our case, with our proposed solution, where the HAPS always on the top of the optical gateway station, obviously alpha and beta remain insensitive to the change of zenith angle because the HAPS always on the top of the optical gateway station. Now, with this very simple proposition, we'll show that we'll achieve great gains. But on the top of the fact that we assume that we have a relay, we assume also that we have a backup RF link just in case the FSO link, even if it is relayed and it fails. So this is kind of a so-called hybrid, basically FSO RF transmission systems where the FSO link is going through a relay. In our work, we assume the HAP performs equivalent forward, that the FSO link by default is used, but if the FSO link is affected by atmospheric turbulence, then we switch to the RF link. We assume gamma-gamma type of turbulence for the FSO transmission and Rayleigh fading for RF transmission. Now, you can look at the paper for detailed mathematical analysis, but the key kind of aspect I want to show is the kind of huge gain that we can obtain with our very simple proposed approach. So if you look at the alpha probability as function of average scenario FSO link, so the green is kind of the benchmark where you just hybrid FSO RF, and then the previous paper was proposes hybrid relayed network with FSO RF that gives you a 4 dB gain. Now, with our approach, by putting the relay always on the top of the optical gateway station, you get already 19 dB gain compared to the reference, or if you will, a 15 dB gain compared to the proposed HAPS relay type of system. If you add to that an RF backup link, you get an extra 2 dB gain. So altogether, you get 21 dB gain compared to the basic direct hybrid FSO RF link between the ground and the satellite. And same kind of gain is observed when you use basically as a metric the average similar to average probability of error. And you can see that this gain is, you look at the right-hand side, you can see that our solution is insensitive to zenith angle. That's the proposed solution, whereas other solutions are the blue and green are very affected by the zenith angle. Now, just to conclude on our proposed approach, we can add to our system a kind of direct FSO link. So we have a 3 diversity type of system. We have a relayed FSO link. If it fails, we go to a direct FSO link. If it fails, we go to an RF link. The idea behind the fact that we put a backup FSO link to the relayed FSO link is that ideally, we want to maintain as much as possible FSO connection because FSO comes with a higher speed than RF. And we want to really switch to RF to maintain connectivity only if we know that there is no chance whatsoever to get an FSO connections. So this extra, of course, capabilities come at an extra cost, but provide some extra gains. What we notice here is that for a low zenith angle, the integrated SATCOM system can give great gains because essentially it has this extra diversity gain coming from the direct FSO link. But obviously, as zenith angle increases, this backup FSO link become less, let's say, reliable because it has to go through a very long path. And in that case, our proposed solution is good enough by itself. But for a low zenith angle or relatively low zenith angle, this extra link can provide some extra gains. And then as a final kind of curve showing the advantage of our system is the probability of RF link usage, because we want this probability to be as low as possible, because the more you use the RF link, the lower the data rate you are going for. So obviously, our integrated SATCOM system is a system that uses the least the RF link, and that's good, because most of the time is operated on the FSO links, either the relayed one or direct one, which means it provides high speed connectivity most of the time. Our initial proposition always use, it has a fixed kind of probability of using the RF link, whereas the other previously proposed systems tend to switch very often to RF link, which means they lose in speed quite often. Let me now wrap up my talk by talking about the access aspect. As I mentioned earlier, one of the challenges behind this network in rural environment is the lack of a reliable power grid. And as such, there is an interest in relying on renewable powered access points in rural areas. So one of my students, PhD candidate Murilo Matrashia, proposed to use essentially or take advantage of tall wind generator in rural areas and attach to them access point, or if you will, base station, in order to provide connectivity in rural areas. As you know, this wind turbine tend to provide line of sight condition over large area without any payload constraint, because they tend to be big given their height. So obviously, I mean, this wind turbine has to be connected to the network. This can be done by putting, let's say, some satellite VSAT close by and have this wind turbine interconnect each other in integrated access backhaul fashion. Or we can rely on this interesting robot developed by Meta or Facebook, if you will, which is known as Bombix, and essentially the job of this robot to wrap optical fiber onto power lines. So optical fiber, I mean, obviously power line will be there in a wind turbine type of environment. So if you wrap optical fiber around that, you can connect this wind turbine to the to the internet backbone, and then the wind turbine having access point attached to them can provide connectivity to this rural area under their coverage. So to make a long story short, obviously we want to see where we can use this type of network, and obviously the best way or the best location where we can deploy this kind of wind turbine based network is an area that are benefiting from favorable wind statistics. We looked at different parts of the world, and there are many databases showing wind statistics. So identified 3 case scenarios. I'll present only 2 here: France, Western France, Southern Argentina, and Ethiopia. And that's the kind of areas we studied in our paper. So let me show you, for example, so this is the map of France on the right. And as you notice here, the more red it is, the better are the wind statistics from a wind turbine placement perspective. So we looked at this particular region in Brittany, in the western part of France, and indeed we found out that there are many already wind turbines based on the database we were able to access. So we select a subset of the wind turbines and attach to them access points, and we looked also at population density in this region based on the Facebook high resolution population density map that have been developed by the Connectivity Lab of Facebook. And what we showed in our studies is if you don't use any access point on wind turbine, you can rely on just existing cellular network. You have this kind of performance in terms of data rate per user. But if you start using what we are proposing on some of the existing wind turbine, you can increase quite a bit the average data rate per user. And then if you kind of pick some extra wind turbine in location that have not been already served with wind turbine. In other words, try to select carefully some location based on population density, where there is higher population density. In these particular areas, you can further increase the average data rate. Same study has been done in southern Argentina, where again, you can see some region with very good wind statistics. Here, the existing wind turbine have been kind of placed in the same location. It was not a good idea to use the 3 of them, so we select only one of them, and we picked few other location to propose new location for wind turbines based on the density of population in that particular region. And what we notice is that by doing that, again, we can increase quite a bit the average data rate in that particular region. Finally, one thing I would like to emphasize is when you invest in research and trying to connect more people, actually you are investing by default in resilience, because many of us who benefit from good connectivity because we live in highly dense urban environment, we may lose this connectivity anytime because of a disaster. People who are enjoying good connectivity but end up in a crowded area, like in a concert or football match, they can also lose connectivity. So that's an area where resilience is important also. If you're sending some scientists in the middle of nowhere and you want them to kind of keep streaming information from the Amazon or from the Antarctic, you are also trying to connect these unconnected people in remote areas. Of course, military mission typically operate in some of these unconnected regions. So when you want a resilient network that can operate in any kind of environment, in any other kind of conditions, obviously you need to connect these unconnected people. And typically you will rely on so-called on-demand pop-up networks. And when you talk about pop-up network, it can be, for example, on the ground, a network that relies on this system that have to find a backhaul on the fly, you have to find the spectrum approach to access the spectrum of a particular region. Power often is an issue, so you need to have your own renewable source, and you want the whole thing to be deployed quite fast. So what we proposed recently is to use this kind of pop-up network in the form of drones. So let's assume you have a disaster that affects a particular region in red here, and in this particular region, your base station that used to be there to cover that region get destroyed, so they're not operational anymore. So in order to kind of to help that region maintain connectivity, you can send some UAVs The question we ask ourselves, based on stoichiometry-based analysis, what is the density of UAVs you need to send, at what height this UAV need to operate? To make long story short, what we showed is that obviously there is an optimal number of drones you can send or UAVs given a particular radius. And then actually also given a particular radius of the disaster, the bigger is this radius, the better you should go for high altitude platforms. In other words, when the radius become huge, sending 40 drones is not as beneficial as sending just a single HAPS, because a single HAPS, a high capacity single HAPS operating the stratosphere, can give you the footprint that you need to connect all these people within that particular coverage area. So with that, I would like to thank you, and I will be happy to take some questions.
Thank you very much, sir. So we have a couple of questions from our participants. So I'll just read out those questions. So there is a question from participant that this work is using different links for connectivity, which makes to establish perfect channel information. So how can you reduce channel state information complexity?
So not all schemes require channel state information. I mean, the communications have evolved over the last few decades, and acquiring channel state information is embedded in many of our current communication schemes and protocols. So what I'm proposing here is nothing unusual. We are not asking for something more different than what has been used. So for example, when I'm talking about these FSO-based links, where you need some switching, obviously you need to estimate the CSI, the quality of the channel, and switch to another channel when the channel is not performing as expected. And that's a classical channel state information is acquired in current network. So this is nothing unusual or not something that we don't know how to do.
Okay, sir. Thank you. And one more question from the attendee. So, for example, we have this 4G to 6G will increase the radiation, which will affect the human health. So, due to this higher frequency ranges, like millimeter wave frequency ranges are in terahertz or in gigahertz. So, what are the radiation detection techniques for millimeter wave or maybe for higher frequencies?
Yeah, this is an important, of course, issue. EMF radiation is an issue that is, of course, of concern. What I can say is all the studies have been done so far are showing that essentially all networks that are being deployed are operating within the allowed thresholds set by ITU and different agencies worldwide that are trying to monitor EMF radiations. But obviously, as we grow to higher frequencies or to unknown region of the spectrum, more studies have to be done. And when I say more studies, we can talk about two fronts. In front number one, we need some of our colleagues in the area of biomedical engineering or bioscience in general to further characterize the effect of radiation on the human body, especially when you go to millimeter wave or terahertz, because we know that from, let's say, ionizing, non-ionizing perspective, going to higher frequency is not to hurt us, because as long as we operate below threshold, because we are still way below the ionized part of the spectrum, and here I'm talking about X-ray or gamma rays, where indeed radiation become dangerous. But even millimeter wave or terahertz, we're way below this ionized part of the spectrum. But what I'm saying for the people who can do research in this area is to try to explore other aspects beyond this, again, ionized, non-ionized thermal effect or heating effect on our body, but maybe other biological mechanisms that are affected by this high frequency. So there is indeed a need to do more research in that front. But on the other front, from a telecom engineering perspective, I believe that we need to invest more into research for what I would call EMF-friendly or EMF-aware networks, which means networks that can perform up to expectation with the KPI that we are after from a speed perspective, from a coverage perspective, but with the lower EMF radiation. And there are ways of doing that. It's a little bit, I didn't have a chance today to talk about this, but we do have an active research project in my research group where we try to develop using, for example, intelligent reflecting surfaces or using drones to minimize EMF radiation in some particular areas while maintaining quality of service.
Thank you, sir. So there is another question from Nasir. So he's asking, how do we measure time delays in satellite communication?
Sorry?
How do you measure time delays in satellite communication?
Oh, so I mean, these are kind of well characterized. Depends on the altitude or of the orbit, right? So if you are at geostationary location, which means that you are at 36,000 kilometers, you know, just looking at the round trip by using the speed of light type of reference point, you realize that you really need 250 milliseconds roughly for a round trip with the geo satellite. Whereas if you are doing operate with the LEO at 500 kilometer altitude, which is much lower altitude, then obviously the delay would be much shorter in the order of few milliseconds. So it's very much depend on the altitude of the satellite to which you are connecting.
Okay, sir. So there is another question. So the bandwidth of radio frequency and optical communication is different than how such integration is being made.
Yeah, that's a very good question. And I try to convey this idea. Ideally, of course, you want to maintain as much as possible connectivity through FSO or optical because the band is much higher. But at some point, you know, you will have to give up FSO link because it can be affected by turbulence or weather condition. So in that case, you switch indeed to a lower speed RF connection. So the RF connection cannot match the data rate of an FSO link, but it can maintain connectivity. So in other words, we have a graceful degradation for maybe a few minutes or a fraction of an hour until this bad weather condition pass, and then you can go back to an FSO link. So it's better than having nothing. So your RF link will give you a backup link at a lower speed, but it's there at least to maintain minimal connectivity.
Okay, sir. Thank you very much. Sir, I think there is a couple of questions from our panelists. So Dr. Satish Tiwari will take over. Yeah.
Okay.
Thank you, sir. I have a question, sir.
Sure.
I'll just speak.
Sir, please throw some light on the communication paradigm, which is better for the in vivo diagnosis. Specifically, which is better communication paradigm for healthcare application? Is it molecular communication or terahertz communication?
For health, what do you mean by health?
Healthcare applications, sir, like to study some in vivo diagnosis, we need nano networks inside this human body.
Yeah, I'm not an expert in this area, but of course, it's a booming area, the so-called Internet of Body Things. So there are multiple ways. I mean, inside the body, people are even talking about molecular communication, where we are doing some even drug delivery through molecular communication. So you know, that's kind of an interesting research area. But even I would say when you talk about connecting the body to the outside world, you may have multiple options. Let's assume if you have an ECG monitoring system with the 12 lead probes. So one approach would be to make every probe connect to the smartphone or to the device to collect the ECG signal. And you'll have to deal with the interference coming from all of these nodes trying to communicate simultaneously with the access point. Or you can have a propagation within the body, create a relay in the body, and that relay is in charge of coordinating the communication with outside access point. So I know that one of my colleagues, I have been in a committee of a student in my university, and one of my colleagues has been working on this paradigm, and he has shown that using cooperative type of communication, where you have essentially a relay on the body, is more favorable than trying to make all the nodes communicate to the access point. So trying to centralize information in the body through kind of a relay in the body while signal propagate over the skin of the patient, and then you can use a short-range millimeter wave link, let's say, can be a good solution to go. But you know, I'm not very active in this area, but you know, that's the rough idea I have on this domain.
So since there are no questions, so I will You have a question? Yeah, please ask.
Nice to meeting you. Nice to hear your talk, Professor. It's a great pleasure for us to listen to your talk. And I have only one question. Right now, the OTFS and IRS modulation technique, IRS schemes are coming. Is it this IRS is practically possible? Or because we are trying to do research on this, like a channel estimation on IRS and like that. So is it valid or is it possible practically we can see anything, sir?
Yeah, so like any research breakthrough in communication, things start by some hardware breakthroughs. And definitely there is some breakthrough in terms of meta surfaces that have been achieved over the last few years that kind of led to people from the communication telecom research community very much interested in IRS. Because IRS is going to be acting as reflector, so it can help essentially creating these passive relays. So from a theoretical standpoint, the potential is huge, it's great. Of course, there are some important practical considerations like channel estimation, like phase shift discretization, and so on. Now we are in this second stage. So when people start work on this IRS in 2018, 2019, that was the time where basically it was booming as a concept. And when it's an interesting concept, people kind of neglect some of the assumptions or practical considerations, and look at the potential. But now we are at this phase 2, where people are trying to address practical considerations, and there are a lot of interesting ideas being proposed to discretize the phase, to estimate in efficient way the channel. So now is the final words out there? Probably not yet, right? But I think it's an area that still is having quite a bit of momentums. Is it going to be fully successful? And by fully successful, meaning by that is to be part of beyond 5G and 6G in practice, maybe in certain scenarios where basically can create some interesting non-line of sight kind of alternative in certain highly kind of let's say rich scattering environment. Maybe it can be an interesting kind of research direction that indeed IRS may become the way to go in future deployment.
Thank you so much.
Professor, there is one final question from Vijendra. So we know in free space optics, link distance affects the data rate. So in such case, how satellite free space optics will surpass the data rate delivered by RF link? So how much extent this free space optics is feasible? Yeah.
I mean, the main problem of free space optics is not really the range. It is because you can collimate the beam, you can make it very energy efficient, and you can reach a geostationary satellite, believe it or not, with the right amount of power. The problem is how much you go through a turbulent environment. So if you're going through very long distance turbulent environment, of course, you will have a lot of scintillation. But when you go to space, you know, the atmosphere, like the atmospheric layer is just in the lower part of the distance. Of the kind of propagation path of the signal. But after that, in free space, basically, and that's why free space optics is a great technology to interconnect satellites that are 100 kilometers apart, okay? Because they are in the outer space, there is no atmospheric turbulence when you're dealing with inter-satellite links. But on the ground, because you'll be going through atmospheric layers, of course, you are limited by first of all, line of sight, and by the fact that you have to go through this turbulent environment. But for space, there is a great potential, and there has been demonstration of connecting ground to even geostationary satellite at 36,000 kilometers.
Thank you, Professor. So Dr. Satish Tiwari will take over. Yeah.
Thank you, Professor, for delivering an informative and wonderful talk. Once again, on behalf of SRM University, FDP Committee, and the Department of EC at SRM University, we thank you for your active participation and cooperation to deliver this keynote talk. We'll be looking forward for this collaborative research with you, sir, if possible. And once again, thank you very much, sir.
Thank you. Thank you for your invitation and thank you for involving me in your faculty level program. Thank you again.
Thank you, Professor Aloni.
Thank you, Professor.
Excellent, very inspiring. We would like to have continued association with you in one way or the other.
Thank you. My pleasure, always.
Thank you, sir. Thank you, VC, sir. Thank you very much for your presence.
Thank you.
And we are having a FDP from 2 p.m. to 5 p.m. This is for the participants. So you can join the session after the lunch break. Yeah. Thank you, VC, sir. Yeah.
Thank you.